Hello guys and welcome to another calculus video. In this video we're going to be taking on this nice integral right here. And I think that's pretty much it. Let's just jump right into it. So immediately right off the bat we have cosine x minus cosine x squared over x times ln x. Now whenever I have two functions that are subtracting each other and then multiplied by some power of x and ln x, I immediately start thinking about the mellin transform. And in this case we can easily take the mellin transform of cosine of x or cosine of x squared using Ramanujan's master theorem. So we're going to go ahead and do that. And then once we apply that mellin transform, we can take the derivative of the mellin transform to get this natural log of x, and then take the limit as s goes to 0 to get that 1 over x. So we're using the mellin transform of cosine of x and cosine of x squared from Ramanujan's master theorem and from the power rule. And so we can define this function I of s, the integral from 0 to infinity of x to the s minus 1 times cosine of x minus cosine of x squared dx is going to be just this function minus this function. We can also differentiate this function I of s to get I prime of s, and we get this natural log of x out in front. Then we take the limit as s goes to 0 of I prime of s, and then this will become x to the negative 1 right here. And so now all we have to do is evaluate this limit over here. And this is pretty nasty since it is the derivative of this function right here, and we get a lot of product rule stuff, but we have a lot of fun tricks that we can use to go ahead and evaluate this limit. So my favorite trick for evaluating limits of the gamma function is you find the Laurent series of the gamma function, and this actually makes the limit way easier. So first, we know that the limit as s goes to 0 of s f of s equals the limit as s goes to 0 of gamma of s plus 1, which is just 1. So that means that gamma of s has a first order pole at s equals 0 because, first of all, the limit as s goes to 0 of gamma of s is just infinity, but when we multiply by s, it gives us a finite number, finite non-zero number. So that means we have a first order pole. So that means gamma of s is going to be 1 over s, that 1 just comes from the coefficient right here, plus a0 plus a1s plus a2 and so on and so forth. We can actually calculate the first two coefficients here. We're not worried about anything above that, which you'll see why later. So we're going to find a0 and a1. Now a0 can be found by the limit as s goes to 0 of gamma of s minus 1 over s, and the reason this works is because if we see gamma of s is going to be equal to 1 over s plus a0 plus a1s and so on and so forth. So if we take the limit as s goes to 0 of gamma of s minus 1 over s, we get the limit as s goes to 0 of a0 plus a1s and so on and so forth. And all these terms other than a0 just go to 0 because they have an s next to them, right? And so that's going to go to 0 as well, and we'll just get a0. So we just have to evaluate this limit. So this is the limit as s goes to 0 of s gamma of s minus 1 over s, or the limit as s goes to 0 of gamma of s plus 1 minus 1 over s. We use L'Hospital's rule because we have a 0 on the top and bottom, and we get the limit as s goes to 0 of gamma prime of s plus 1, which is just negative gamma. So that tells us a0 is negative gamma. We're then going to do the same exact thing to find a1. It's the same exact trick right here, just for the next term, so we need to find this limit right here. We again put everything over s squared, just to get everything on a nice common denominator, and then we replace s gamma of s with gamma s plus 1. We differentiate using L'Hospital's rule, and we actually have to do that again, and we get that we have the limit as s goes to 0 of gamma double prime of s plus 1 over 2, which is equal to gamma double prime of 1 over 2. And so now we need to calculate gamma double prime of 1. So the way I'm going to do this is I'm going to write that digamma of x equals gamma prime of x over gamma of x. I'm going to go ahead and differentiate this. So I get gamma, trigamma of x, trigamma of x equals gamma double prime of x over gamma of x minus digamma of x squared. This just came from the other product rule term. And then when we plug in x equals 1, we get that pi squared over 6 equals gamma double prime of 1 minus gamma squared, or gamma double prime of 1 equals gamma squared plus pi squared over 6. So this means that our Laurent series for gamma of s is 1 over s minus gamma plus gamma squared over 2 plus pi squared over 12s. And I'm just going to call this term right here alpha, because it's going to make our calculations a lot easier. And of course we have higher order terms that we're going to ignore. So we're going to split up this limit into 4 separate limits. The first limit is this term right here, the second limit is this term, and the last limit is going to be these two terms taken together. So to evaluate the first limit, what I do is I plug in for gamma of s, I replace it with 1 over s, and I plug in sine of pi s over 2 with pi s over 2. And what I did was I just took the first term in the expansion of each function. So this is the first term in the Taylor series of sine pi s over 2, and the first term in the Laurent series of gamma s. And notice that we actually don't need any additional terms, because if we add more terms onto that, for example, if we wrote 1 over s minus gamma, this actually would not help us at all, because that gamma term would just get multiplied by pi s over 2, and then when we take the limit as s goes to 0, pi s over 2 goes to 0, so it would just cancel and become a 0. And the same goes for adding extra terms in the expansion for sine of s. It doesn't really help us, because those extra terms will just be multiplied by a power of s, and so they'll go to 0 when we take the limit as s goes to 0. So overall, this limit is negative pi squared over 4. We're going to do the same trick for this other limit, almost the exact same thing, just now we have 2 over s and pi s over 4, so we get pi squared over 16. Next, we're going to need the expansion of gamma prime of x, and we're going to use higher order terms in our series. So if gamma of s is 1 over s minus gamma plus alpha s, then gamma prime of s is negative 1 over s squared plus alpha, plus other terms as well. So now we're going to go ahead and do that limit again. So in this case, we're going to use the first two terms of the expansion of gamma prime of s and of cosine of s. And again, if we add any additional terms afterwards, they'll give us terms with positive power s, which will go to 0 anyway. So we get this right here, and then we just have to go ahead and expand it. And notice that beautifully, all our divergent terms with that 1 over s squared cancel. These terms with a coefficient of s squared also go to 0, and we end up with 3 alpha over 4 plus 3 pi squared over 32. And then our overall integral I, we just have to add the results of L1 and L2, and we get this nice expression right here, which ends up simplifying to 12 gamma squared minus pi squared all over 32. Thank you so much for watching the video. I hope you enjoyed this nice problem, and I hope you learned a little bit about how to evaluate limits of the gamma function. Thanks for watching. I'll see you next time.